Once upon a time, there was a piece of data. When we gathered more, we began to notice patterns. Mathematicians invented ways to describe those patterns, like the mean and the median. Then in 1805, a powerful idea was born, the regression analysis, using which we could draw a curve that fit the data so well we could use it to predict the output for a new input data. But here's a thought. What if instead of just using equations, we tried to mimic the human brain? In 1958, the scientists created the perceptron, an artificial neuron. It took in signals, applied weights, and fired an output, just like the neurons in our brains. Connect enough of these single layer perceptrons, and you could classify things, like telling if a sensor reading was normal or abnormal. The catch? They could only solve simple linear problems. After a period of sluggish progress called the AI winter, in 1986, the multi-layer perceptron arrived. Now, the outputs of one layer of perceptrons could be fed into another. Such a network of neurons, called the neural networks, enabled us to solve complex and nonlinear problems. It became a useful pattern recognition machine, good at predicting statistically likely output for unknown inputs. It could recognize patterns far beyond simple math could. But what if we wanted these networks to work with language? We'd first need to turn words into numbers. Early systems simply gave each word in the vocabulary its own vector, a kind of ID number for every word. That helped, but language is more than single words. It's sequences, sentences, context. In 1997, a breakthrough appeared: recurrent neural networks. At any moment, they remembered not just the current word but also the state of the words before it. This let them learn patterns from whole sentences and predict the next word with memory of what came before. Of course, to train these networks, we need data, a lot of it. The internet gave us that in abundance. But training on so much data was painfully slow until 2012. That's when researchers showed GPUs or graphics processors could train neural networks far faster. Suddenly, we could build deep neural networks with many hidden layers solving problems of astonishing complexity. Still, there was a limitation: how we encoded the words. In 2013, word embeddings changed everything. Instead of representing words as isolated identification numbers, embeddings mapped them into a multidimensional space where similar words sat close to each other, like king near the queen or Paris near France. But meaning isn't just about individual words, it's about how words influence each other in a sentence. For example, based on context, we should be able to understand if the sentence refers to Apple the fruit or Apple the company. In 2017, transformers arrived. Their attention mechanism could look at an entire sentence at once, deciding which words mattered most for each other. This context aware encoding made it possible to truly capture meaning in language. The word embeddings from this attention layer can then be fed to multilayer perceptrons for recognizing patterns in human language. And when we chained multiple transformer blocks together, we got large language models. The first of which, GPT-1, arrived in 2018, trained to predict the next word but with a deep understanding of context and meaning. However, it quickly became important to understand how a LLM constructs its response. By 2022, researchers introduced chain of thought prompting. Instead of just jumping straight to an answer, the large language models could think out loud, breaking problems into steps and explaining their reasoning. The results? More accurate answers and more transparency in how the model got there. It became clear that the large language models are good at providing responses based on the internet data. If we could connect them to enterprise data, they could provide more business relevant information than just internet data. If we could connect them to applications, maybe it can even do some of the task on its own. Connecting the large language models to company data, the APIs, and tools was messy. Each case needed a custom integration. Then came 2024. The Model Context Protocol (MCP) changed that. It standardized the way LLMs could connect to data and tools, unlocking the era of AI agents. Systems that don't just tell you what to do, but can do it for you. And now, innovation in the space continues to move forward. The story is still being written. The next chapter might already be underway. A chapter where the humans and the AI lived happily ever after.